We continue the introduction to Delft3D Wave. And first, let's have a little look at under what kind of conditions we run these swan models. If we're talking about a morphological model, we are typically in a situation where we have tidal motion uh, for which we need to define boundary conditions, and also we have highly variable wave conditions. So are we going to run the model just for every tide and every wave condition? Well, that would be way too expensive, so we'll talk about that in a bit. And then we'll talk about the basic model setup in Delft3D Wave and some general modeling aspects. So if we look at the spring neap cycle, here's an example of how the water level goes up and down. We try to find a tidal cycle that is more or less representative for the spring neap cycle, typically a little bit above the mean tide. And the way we do that, that's a different topic, but in our practice, we typically have one schematized tidal cycle, and at the same time we have waves that can come from all directions and with different wave heights and periods, and we have to reduce that to a representative, to a manageable number of wave conditions. Wave schematization. Here's, for instance, a table of the wave height classes and wave direction classes and their frequency of occurrence. And for each of those classes, you have the representative wave periods. Well, we need to find a way to reduce that whole wave climate to, first we can plot it as a wave rows, but then we have to create representative wave conditions for each of those conditions, and in the end come up with a manageable table of wave conditions, and we have tools for that. But the take-home point now is to realize that we cannot afford to just run time series of waves over the whole year. We have to strongly simplify the wave climate in order to make it manageable. Because we have to do several wave simulations over a tidal cycle to correctly represent the wave current interaction. And then we have to do that over a number of wave conditions. And then possibly also for a number of nested computations per wave call. So in the end, you end up with thousands of wave simulations per year. And since Swan is a computationally, well, it's efficient, but it's still expensive, we need to reduce the number of wave conditions as far as we can. Let's go into an example of how we set up a Delft3D wave and current model. If this is our area of interest, here it's the Ameland Inlet in the north of the Netherlands. Here's the bathymetry with its channels, its ebb delta, and the nearshore area and the deeper sea area. And here is the tidal basin. So if this is our bathymetry, how do we represent the wave and the current models? Well, first of all, in order to avoid strong shadow effects from the lateral boundaries that are not well defined in SWAN, we can create an overall grid that is relatively coarse, and then a nested SWAN grid that has the same resolution as the flow model. And you see that there's a concentration of grid lines in this area and in the nearshore area. to get the resolution where you need it. So if we plot the wave and the current grids, we have the overall wave grid, the nested wave grid, and it's the same as the current grid in this case. We put wind on the whole thing, we define waves at the boundaries, and we define current boundaries over here. In this case, we kept these boundaries closed because they were at the tidal divide. So this, in a nutshell, is the setup of the model domains. And here's some examples of what it can look like. If you plot it with quick plot, for instance, wave height and direction, typical the reduction of the wave height because of the wave breaking here, and a little bit of propagation inside here, but not much. Wave dissipation on the ebb shield and in the surf zone, creating wave forces that are then used in the flow model. And here's an example of the resulting currents in the flow model, which is partly driven by the tide. As for the large scale, these currents are purely tide driven, but the little highlighted currents here, they are wave driven currents. And that's why you need a high resolution, because they take place in a very narrow area, but they're very strong, and they do represent a lot of the longshore sediment transport. Some general modeling aspects. This goes for SWAN or any other model. First, you pick your area of interest in X and Y, and also in the frequency and directional space. You choose your boundary conditions, you choose your resolutions, and then you do a sensitivity study of the numerics. How fast does it converge, etc. Do we have lateral boundary effects? We check the model convergence. Then we do a sensitivity study of the physics, for instance, the breaker parameters, and we calibrate and verify if we have local data to compare with. The accuracy of model results depends on, of course, the quality of the model input. How well is your bottom measured and represented in your grid? The currents and water levels and winds, the waves at the boundary, the physics, and the numerics. The most important thing in setting up a Delft3D wave is the computational and bottom grids, and the wave boundaries. What do you put there? How do you represent the physics, and how do you define your wave parameters? How do you set your numerics, and what kind of output do you create? WAVM is the wave map files. The COM file is the communication file that passes variables on from flow to wave and from wave to flow. Structures in Delft3D wave, you have to be careful using dry points and thin dams. They're not automatically transferred to the SWAN model, so you have to apply obstacles for that, or you have to include the structures in your bathymetry. Now let's go through the Delft3D user interface. This is the typical setup, very similar to that of the flow model, where you have a description, and here are the different data groups. Let's go through especially the grids. So they can be they are in the geographical space. So what are the actual numerical grids, like the flow grid that we are used to generate with the RGF grid. Um, and this can be curvilinear, and it usually is curvilinear. And we also have to define the spectral space, logarithmic or in the frequency, and regular in the direction. So in this menu, you just select a swan grid that you have defined with the Delft3D RGF grid and the depth on Quicken. And this is how it may look. The visualization area, details, you see quite a detailed model here, and possibly a nested grid here. In spectral space, you can define only a sector or the full circle, and if you then define 36 segments, then you have 10-degree resolution. The frequency space, where you have somewhere between the lowest frequency, typically something like 20 seconds, 0.05 hertz, and the highest frequency, about 1 hertz, which is typical for waves between 5 and 10 seconds. You have to realize that if you have a very narrow directional spreading, then you have to also have a higher resolution in your directional space than when you have a very wide WinC spectrum. The resolution in the frequency space is typically taking between half the peak frequency and 2.5 times the peak frequency. That is the most interesting part, which the model can actually resolve. The swan grids, they obviously need to be fine enough to resolve the relevant spatial details, and we typically take them the same as the flow model. Water levels from flow and currents are interpolated to the wave grid, and the results from wave is interpolated back to the flow model. Directions can be in nautical convention, with direction relative to north, where the waves are coming from, or in Cartesian convention, where the waves are going to. The boundary conditions can be defined in different ways, but the easiest way is to do it by orientation and just make sure that you check if the swan interprets that in the right way. You can have all sorts of complicated spectra at the boundary, but you can, and they can be variable along the boundary. But for morphological runs, we typically just have constant boundaries where we have the boundary at the depth contour, so it's reasonable to have constant wave conditions there. And we define them usually as parametric boundary conditions. And that is then through a significant wave height, a peak period, a nautical direction, and the width of the energy distribution. The physics, we would usually use third generation, the best kind of representation of your wave generation and propagation. Depth-induced braking using the Batjes and Janssen model. I would say, typically activate the bottom friction with a the John Swap model and deactivate the nonlinear triad interaction because they are not extremely reliable in SWAN. Numerics, the most important thing we play around with is the percentage of wet grid points and the maximum number of iterations. The other options are typically kept at default values. And you can define your output of wave characteristics on your different computational grids. And you can also output the flow model and select a grid file for your flow model to make sure that the data is transferred to the flow model. Here's an example of a combined wave and flow model for the Willapa Bay in the northwest of the United States. And you see this modulation here is due to the tide. There's a shallow area here, and the tide has an enormous influence on the wave propagation, but also what you see is now and then there's a storm and the waves increase here. So it's also variable boundary conditions here in time. A bit about wave current interactions, the processes affected by waves and the wave current interactions, how to include the waves in the flow GUI, and examples. So what happens if you have waves in your flow model? What happens is an enhanced vertical mixing due to turbulence generated near the surface and near the bottom. We have a net mass flux which affects the current profile, especially in the crossshore direction. This is mostly in 3D. In the surf zone, we have a longshore current and a crossshore setup due to variations in wave-induced momentum flux. This may cause rip currents. And we have an enhanced bed shear stress. In the wave current interactions, there's very complex methods to describe the bottom boundary layer under combined current and wave action. And these are schematized in these different models, of which Fredso 1984 is the default that we choose. This is how to define the waves in flow GUI. You have to select the wave process under the processes, and also you have to define the bottom stress formulations due to waves. And then flow and wave communicate through a communication file that can be recognized as com hyphen run identification .dat and def. And the whole thing is an iterative process where the wave module produces wave forces and orbital velocities, passes them on to the flow module, and the flow produces water level and currents and passes it on to wave. Here's a case for a rip current where you have a bar but a gap in the bar. And if you zoom in, you see here, so waves are breaking here and the flow can escape through this gap. Or what does it look like? We have start with a uninterrupted flow, and then because of these wave forces, the flow gets diverted, and this diverted flow again influences the wave pattern. So after a few iterations, you end up with this kind of of pattern, with a longshore current that is here. So these are pretty oblique waves, and there's a strong wave-driven current on the bar, but then it gets a strong offshore component here, which is extremely dangerous for swimmers. Just to illustrate the point about structures and how to deal with them in in flow and swan. So if you have a thin dam in your flow model, you need to put an obstacle at the same point in your wave model. And the tip is to create a polygon first, defining the structure, and use it both to define the thin dam and the obstacle. And then you're sure that they're in the same location. We're going to create a test case for a straight coast with a wave model of 1 kilometer by 4 kilometers in the longshore. The flow model will be half the size in the longshore direction to avoid the boundary disturbances in the wave model. We'll make a grid resolution of 20 by 50 meters and a bottom slope from 10 meter depth to -1 meter depth, with waves of 2 meter, 7 seconds, 240 degrees. And what we will do is we'll start making a wave model only, then test the extent of the boundary disturbances. We select a flow grid based on this. We cut out this flow grid, set up the flow model, set the linkages between flow and waves, run the combined wave flow model, and check the flow pattern. And then we'll play around with structures and nourishment. So that'll be the next exercise.